Well, welcome back, everyone. Today we're on session 27, and our topic is material selection. But as we've been doing, we're going to have a little brief schedule review. We have completed the exam last time. We haven't graded it yet. I'll probably do a message to tell you what the average standard deviations were, and there'll also be a video posted on solutions to the exam problems. So here we are today, and just to remind you, immediately after the exam, start on working on the team mini project. There's about 7 or 8 days really on that project, so I don't want you to get too stressed out about it. It's a very short period of time, so please just do the best that you can. When you are completed with that, would like you to submit that. There'll be an assignment on Canvas, so you can submit it in a normal way. This is a team project, so if you're on a team with several other people, only one of the team will need to submit that. And I just wanted to mention, as you're considering the project, you can use other materials than steel. We're going to be talking about ways to select material today, so you can apply some of the learnings of this session. You can also change from the internal combustion engine, which is in the package drawing, and create a battery electric vehicle. Will be some resources to help you do that if you decide. There's a guest lecture video talking about some of the differences between a battery electric and an IC vehicle, particularly for the body structure. And then there's also going to be posted some battery sizing information that'll tell you, given a range, how big of a battery should you have. What we're targeting is that on August 14th that the project will be due. And I do want to mention one other thing, that these 2 lectures, we will have a very brief online quiz in Canvas. There'll be more instructions about that later on, but that quiz will be ready to go at the end of lecture number 28. So that's a 10-minute or so at the most quiz. Okay? So let's start with the topic for today, material selection. How do we know what the best materials are for different areas in our body structure? So what we're going to start with is just some examples of alternative materials in our auto body structure, going beyond just kind of regular steels to some advanced high strength steel grades, aluminum, carbon fiber reinforced plastic, and then an idea of not just a homogeneous structure of one material, but a multi-material body structures. So we'll go through those examples, and we'll talk about mass benchmarking. How much mass change can we expect when we go to other materials than steel? We'll look at some of the relative properties of the material options that we have, and then we'll come up with a kind of a nice procedure for selecting the best material for a given application, again, very early in the design process. So let's take a look at what are the material alternatives that we have in auto body structure. First of all, just considering the single material family, so a homogeneous structure, we'll be looking at some high strength steel grades first. We'll be looking at a couple of examples of aluminum applications, and then rarely is the whole body made out of magnesium, but we do have an example of instrument panel beams in magnesium. So these are the single material families. We also have multi-material families. We'll look at just a couple of examples there. One is carbon fiber reinforced plastic and aluminum multi-material, and then another is aluminum and steel, kind of all mixed up into the same structure. So first we'll look in this area of ultra high strength steel grades. A couple of examples here. This is the Ford Edge. This is is a 2015 model. But what we want to look at is the pie chart of steel grades within the vehicle. So you can kind of see that mild steel, which is kind of what we have been using or assuming throughout the course, is a relatively small but important fraction. We can kind of see that we have some other super high strength steels, martensitic boron steels, dual phase. This is the tensile strength, and then high strength low alloy steel. So when we talk about a steel body structure, we're really looking at several different steel grades used at the appropriate place in the structure. Here's an example of a pickup truck, this Chevy Colorado, and same idea. It isn't just one single steel grade; it's a mixture of many. And one of the things we're going to talk about is how do we know, what's the best place to use some of the higher strength steel grades. Basically, the applications of the higher strength steel grades are motivated by mass reduction. And just to give you a feel for several different vehicle programs, this is going from one model year to the next during a redesign. Kind of considerable amounts of mass reduction, in part, not wholly, but it's attributed to the use of advanced high-strength steel grades, and then that idea of secondary mass change and compounding that allows mass to be taken out of other areas of the car. So this can be quite significant. In the last lecture, we looked at some of this. We won't go back into detail on this, but if you remember, we were looking at the side impact loading, particularly of the B-pillar, which is the major load path, and the need that we would like a very high plastic moment, and that plastic moment is a function of the tensile strength of the material. So we need that high strength in order to have a reasonably sized structure. So we want to choose the steel grade with the highest tensile strength. And again, this is kind of a review of what we talked about last time. We need both good formability to make the complex shapes here in a press form, and we talked about last time in a kind of a cup height test that cup height going up in this direction, that we can kind of push a sample upwards before it fails, is directly related to the total elongation of the material. Okay, so we go from more stretch, so this is better formability of the part. We want to be up here, and we can kind of see here that we also need really good total elongation as a material property in order to achieve that. So when we look at the high strength steel grades, we can kind of say, well, for the functional aspect, we want to be out here, very high tensile strength. But unfortunately, the nature of steel is that there's this relationship between tensile strength and maximum elongation. So if we want really good formability, we're kind of stuck with relatively low tensile strength steel. If we want good tensile strength, then we're kind of stuck with making it out of very simple parts because we can't get much elongation in the material. And this is a whole idea of the so-called advanced high-strength steel grades, that they kind of break this trade-off and kind of raise that curve upwards and to the right. And we saw last time that idea of hot forming a particular chemistry, boron steel, that we could form it hot, have really super good formability, and yet when it's cooled down, have ultra high strength as well. So that's you kind of want to think particularly of this chart when you're looking at selecting different steel grades. Okay, so let's move on to aluminum. A couple of examples here. One is the Audi A8. It is has lots of aluminum in it. So you see quite a few aluminum parts. The steel is basically just the hang-on panels, things like the bolt-on, perhaps fenders or so. So this is largely a homogeneous structure made of aluminum, and this is showing the various manufacturing processes in order to get the shapes. Below we see kind of a famous example now of the Ford F-150. The cab of this truck is almost all of aluminum that you see here. The color coding is the yield strength and the tensile strength of the materials. The only exception to aluminum on the 150 is the dash panel, and this is basically motivated by sound transmissibility. And the other is that it has a steel chassis frame as well. That is, interestingly, again, some of the advanced high-strength steels in that frame. So the main highlight of aluminum is how do we get the shapes. There are many parts that are stamped in a process very similar to steel. Although aluminum requires shallow or draw depth, it isn't quite as formable. It doesn't have quite the elongation that steel does, and we need to have kind of a gentler shapes, things like larger radii. Extrusions is a really neat process, not available in steel really, but when we have kind of a linear element like you see here, we can just kind of squirt that out and get some very complex shapes that we couldn't achieve very easily if we were trying to stamp these. It's a relatively low-cost tooling in order to get the shapes. That's relative to stampings where we need the match dies. The tooling life is relatively low, so this is often used for low-volume vehicles. And often there's post-forming steps necessary. For example, once we kind of squirt out the shape, we have to go in and add holes or bend the part into the ultimate shape that we want. The other area available in aluminum, generally not available in steel, is this idea of die casting. And this is an example of a die-cast hinge pillar. So if you remember from our discussions with steel, this would be a multi-piece stamping, which would have to spot weld together. So here we just have one piece coming out of the process. We do still have pretty good ductility in these die castings. We can have thickness variation throughout the part. So unlike a stamping where we go in with generally a single sheet, we have a uniform thickness. We might have a Taylor blank where we can get multiple stampings or thicknesses, but not too often. The other interesting area here is we can add stiffening ribs like you see here in order to prevent buckling primarily and to increase the rigidity of the part. So these are the interesting processes with aluminum, a little more wider range of options that we have. As far as a comparison of material properties, this takes the same chart that we were looking at before, elongation versus tensile strength, and then plots the area of aluminum alloys here. So you can see generally aluminum is a lower strength material and has slightly lower elongation than steels. Let's take a look at a comparison of not only the structural performance but also the cost. In general, from a material standpoint, so this is just looking at material here. Young's modulus in aluminum is about a third of that of steel. The density is about a third that of steel as well. Okay, so it looks like it might be just a wash if we tried to use it. However, if we looked at a rectangular section in bending and said that, well, our criteria is equal bending stiffness for these two parts, what we would find is that the relative proportion of the steel and the aluminum beams would look something like this. I think if you maybe remember when we were looking very early on about the performance of optimal rectangular sections, we came up with a particular size for steel. If we did that in aluminum, we would find that it's a little bit thicker than what we would see in steel, 1.7, and the height of the section needs to be a little bit higher to take full advantage of the steel properties. And where that leads us is that the mass in aluminum is about 2/3 that of steel, for if we're looking for the same bending stiffness. We'll see later on that the function that we're looking at really kind of determines this ratio here. Now it turns out that the cost for aluminum is about 3 times that of steel. Okay, so this factor of 3 keeps coming up when we look at this. So now let's consider the cost. The cost of a part is equal to its mass times the material cost per kilogram. So if we look at the material cost for aluminum for this optimally shaped rectangular section, we have that it's about 2/3 that of steel. We need to multiply that by 3 times the cost per kilogram, and we're looking at that as a ratio of the cost of steel. And what we find is that this aluminum beam would be about 2 times the cost, the material cost. Okay, we're not talking about processing costs right now, but 2 times the material cost. Okay, so there is kind of a penalty for using aluminum. It can be lighter, but it is also generally more expensive. So let's very briefly look at a couple more examples here. Now we're going over to the multi-material families. There's really not too many cases that we can look at for carbon fiber reinforced plastic and aluminum. The only one that I'm aware of right now is the BMW i3, a little electric car. Here the body structure is carbon fiber reinforced plastic, but that sits on an aluminum frame. Okay, so we have both a little subframe in the front and then a whole chassis frame underneath the rest of the vehicle. So I kind of call that a multi-material car. It's a rigid connection. There are no body mounts on the car, so the two are kind of like an integral structure. The suspension loads through the spring and shock go through the metal structure, so they're applied here and here. And here we see kind of the assembly of the front end of the car, also aluminum onto this carbon fiber structure. Let's look at a few of the sections here, and I just want to mention that we're using A2 Mac 1. It's a body or vehicle teardown a company, so we're taking a look at their photographs and sections here. But here we're looking at the A-pillar and a close-up of the A-pillar, and you can see that the general shapes are really not too much different from what we had looked at before for steel. Here is a section view, so we're going to cut this right here, and we see the carbon fiber section here in blue and in red. It's a little bit thicker than we would use in steel, about 3 millimeters here and here, both 3 millimeters. If that was in steel, it might be something like 2 millimeters. So this is a very critical element for something like roof crush, for example. Okay. So the last one we want to take a look at is aluminum steel mixed multi-material family. The new Tesla Model 3 is a good example of that. It's basically a steel structure. You see the blue, the yellow, and the red in the little picture here are steels, and the aluminum elements here, here, and here are shown in the rocker area, the front barrier loading, and then kind of the whole rear end sheet metal area. Here's another example of a multi-material vehicle. This is the Cadillac ATS. This is a 2013 model that we're looking at. But the main structure is primarily steel of many different grades like we saw. But it has this element here where this is where the strut attaches, and this is a cast aluminum strut tower. So when you think about how do we put together an aluminum part onto a steel body structure, we need to have slightly different fastening processes. And normally the sheet steel would be generally spot welded, maybe some laser welding. But here are some examples of multi-material joining methods. Flow drill screws. So I believe this is on the F-150 pickup truck that we see here. Just kind of spin the screw in, going through the different materials. Self-piercing rivet here. So we just kind of blast a little rivet, making the hole at the same time. And we can also have a high impact rivet, kind of basically does the same thing. But each of these have the ability of joining two different metals together. Okay, so we just kind of did a very brief overview of several of the different options that we see in production today. Let's take a look at, well, what are the mass implications of those elements if we kind of go from aluminum to steel. So what we're going to look at first is the body structure in the subframe. So we're looking at this as a structural system. And what we're looking at here, and just kind of arbitrarily separated this information with respect to model year, we're looking at the body structure mass, the mass of this system. And each one of these dots is a particular vehicle. So on this side we're looking at steel. On this side we're looking either at all aluminum, the red, or mixed materials. Okay. So when we look at it in this way, you kind of hard to see any differences between steel and aluminum. And of course, we kind of can surmise that one of the reasons for that is we're looking at a whole range of vehicle sizes and vehicle gross mass. So let's try to do a little bit of statistical analysis on this data. So what we're going to do is look at some kind of mass drivers. And what we're saying is that the body mass, call this the body structure, is some function of the mass drivers. Okay, so we can look at something like the gross weight of the vehicle. We can say, well, the higher the gross weight, the larger the inertial loads on the body structure. Therefore, the body structure will depend on this. There's a physical reason. Plan view area, we'll just take the width times the length as a plan view area, and it just makes sense that bigger cars' bodies would weigh more. And then we'll finally look at, as a mass driver, the material in these three categories. All steel, all aluminum, or this idea of mixed. And then we'll try to come up with an equation for the body structure mass as a function of these mass drivers. So here's what the data looks like. When we plot them, unfortunately, we can only easily plot two dimensions at a time. So here we're looking at the dependency of body structure mass on the gross mass of the vehicle, and we definitely see the trend line. And here we are looking at steel are the orange dots, blue is aluminum, and then the one example of a carbon fiber is shown below that. And then here we're looking at the plan view area, so we're looking at just the size of the vehicle, how the mass depends on it, right? We'd like to look at this in 3 dimensions, but what we can do is do a regression of this information and come up with an equation that takes all of the mass drivers into account. And this is the resulting equation, that the mass of the body structure system depends on the gross vehicle mass to some power, the plan view area to another power, and then so we can calculate that for a given vehicle. And then if the vehicle is steel, we just multiply that result by 1. If it's aluminum, we multiply it by 0.66. If it's carbon fiber, we multiply it by about 0.5. So here we're kind of getting an idea of just what is the effect of the particular material selected on the mass of the body after we normalize for these other mass drivers. Okay? So we get kind of the idea, just like we said before when we looked at scaling the rectangular section, that it was about 2/3, and here it is showing up again. Really early in the class, we said that, well, the vehicle is basically driven by its stiffness, and that makes this kind of consistent. We can see carbon fiber is the real superstar here at about half of the mass of a steel vehicle. So let's take a look at this idea of plotting benchmark data a little bit more. Here we're going to focus on pickup trucks now. And we're going to look at these 3 categories of pickup trucks, the mid-size pickup trucks, full size, and then the heavy-duty size. Okay? And what we're doing again is drawing on the database from A2 Mac 1. So this is the limited set of information that we have. The Ford 150 we already saw is the aluminum example. So we can do the same kind of an analysis looking at the mass of the cab. The cab itself doesn't have to take inertial loads. Basically, the chassis frame is what reacts those loads. So we're just kind of normalizing here with respect to the size of the cab. And again, we can have these multipliers here. And again, this approximate number of 2/3 the mass of steel for aluminum comes up again. So this is the cab. When we look at the box, we get kind of a different picture. Here we're looking at the box structure mass on the x-axis this time. So we kind of see the values for equivalent all steel versus the aluminum box. So this one is pretty dramatic. This is about 50% of the mass of the steel when we consider it in aluminum, but we just have the one data point right now. Did the same thing for doors. Again, these are the pickup truck doors that we're looking at. Here the main mass driver is just the size of the door in the side view. You can see the relationships. These are the steel in the different categories, the mid-size, the full-size, the heavy-duty trucks. The single example for trucks of a aluminum door. So this is the door structure mass. Okay. So it's just what we're looking at in these pictures. It's just the kind of the metal part of the door without components in it. And we do see here this is now about 0.6 for aluminum as far as the mass reduction potential. What's a little bit curious here is that when we look at the door system, so now this is the built-up door with all the components in it, we can see that there's much less difference for the aluminum door. It's kind of now just kind of one of the cloud of data. So it's a little bit curious because we know that the aluminum structure is more costly. And yet, when you get to the final door system, a lot of that mass reduction just washes away, and it just becomes another door, not particularly light. Here's information on the hood same class of vehicles. We're still looking at the pickup trucks here, but it's very clear. You can kind of really see the very extreme differentiation between the all aluminum hoods and the all steel hoods. And here's that ratio is about 0.55. So when we bring together kind of all of this statistical benchmarking data from looking at different aspects of the A2 Mac 1 database, this is kind of what we see. This is the ratio of the mass of the component in aluminum to steel after we've normalized for the other mass drivers. So now they're kind of on equal footing. So for side doors, other than pickup trucks like we looked at before, we're kind of getting an area like this. And the gray refers to mass efficient design. So these are looking at kind of like the best of the best steel versus the best of the best aluminum. And the nominal just means we're looking at the whole scatter plot, just the average line that goes through the cloud of data. So you can get an idea of kind of the ratio between aluminum and steel. This is that kind of that zone of about 2/3 that we had looked at before. And then the kind of really interesting one is that pickup bed, about 50%. Okay, so now we have some kind of ideas of what are the potential for different materials in real-world application. Let's take a little closer look at the relative properties of material options. Okay, so again, we want to be always looking at these from the idea that we're designing auto body structure parts, and we're saying right off the bat that whatever material we select, the design must meet the structural requirements. Okay, and then we can compare the opportunities with different materials. And our objective is we're going to say it's to reduce mass here. And some of the motivation for doing that, it will reduce fuel consumption. We'll have a lighter vehicle to accelerate, and therefore it'll use up less gasoline or oil or electricity. If we're designing electric vehicles, we'll have a greater range. We'll have improved acceleration performance, better handling with reduced mass. And we just know in general that it's going to reduce the loads on our body structure from the other vehicle subsystems. Okay, so that's why this becomes an objective. Okay, there may be other ones, but this is the one we're going to be concentrating on. And the other aspect is we want to balance the reduced mass with how much the material costs that we're substituting. So we want to talk in terms of kind of dollars per kilogram of mass reduction that we've achieved. So that's based on the material cost. Okay, I kind of don't want to ignore this idea of life cycle assessment of greenhouse gases, of CO2. That as we look at this, when we reduce mass, that reduces fuel consumption, that will reduce the carbon dioxide output during the use phase as we're using the vehicle. However, for many of these materials that are lightweighting, they just take more energy to produce the material. So during the material production phase, there's generally an increase in the CO2. Okay, so we might not end up with a net benefit. So that's the whole idea of looking at the life cycle assessment rather than just an individual stage in the process. So let's look at these properties. Here we're plotting Young's modulus against the density of the material. And in each of these charts that we're going to look at, I just put a little star to show kind of where would the perfect material fall. So it would be, in this case, it would be super high strength or a super stiff high modulus and be at the lowest density. Okay. And as you kind of look at this, you kind of see that as nature has it, there's always this kind of a trade-off. There's kind of a natural trade-off we have to make. That the higher modulus materials like steel happen to be also the most dense materials. Here we're looking at tensile strength. So this chart is kind of looking at the stiffness aspects. of the structure. This is looking at the strength aspects of the structure. And we get the same kind of a general trend. The materials that have the highest tensile strength are also the most dense. Now we're going to bring in the price to this, and again, kind of have the general trend line going up. Carbon fiber reinforced plastic, which is really good for modulus, also has some of the highest price per kilogram. And then finally, here's the CO2 footprint that I was talking about before. So what this is the kilograms of CO2 produced. So we want to minimize that for every kilogram of material that we end up with. And this is the material kind of in the usable shape. So it's like a roll of steel or a billet of aluminum ready to be shaped into a part. So you do see here that kind of the ones with the lowest CO2 footprint, things like steel or some natural materials like bamboo, they're the best for the material production energy, and things like aluminum, magnesium are much higher. Okay? And just note here that these are log scales. So when we talk about this difference between steel and aluminum, it's a big difference. One thing that I wanted to point out on here is that I've added a natural material here, bamboo. What you'll kind of see later on when we start to look at material selection is that some natural materials are really good structurally. They don't seem like they would be, but wood is not a bad structural material if we can kind of get it to work with some of the other requirements that we have. So we have all these material options. Carbon fiber reinforced plastic. The G here is glass fiber reinforced plastic. Nylon, magnesium, aluminum, both lower strength and high strength steels, and then the natural materials. Well, how do I select the best one for a given application? So what we're going to be talking about now is basically how to do that, how to select the best material. And what we're going to be using here is an idea of a material index. A material index is a ratio of material properties. Okay? So if we go in and we'll have a particular material index for steel, we'll have a different one for bamboo as we substitute in their material properties. Okay? So what's an example? Here's an example of a material index. And there's many, there's not just one. And these depend on what the function of the part that we're trying to select a material for. So here is a material index between tensile strength and the density of the material. Okay. So to get a numerical value for this, we'd plug in the values, say for steel, and would come up with a number. We could plug in for carbon fiber reinforced plastic, their properties, we get a different number. Okay? So we'll kind of see how we use those numbers in a minute. But here's another material index. This would be one using Young's modulus and density, so it's kind of a stiffness related one. So the material index equation that we're looking at there depends on the function of the part and which dimensions are free to change. So those are the two things that we have to know. Okay? And this is something that we can derive, so this isn't just an opinion of what properties we should be putting together. We can actually derive it and come up with a number. And what we'll find is that for a given function and for a given set of dimensions that are free, we will always want to select the largest material index, and that will be the most efficient material. Okay? And generally, we'll be looking at what material will give us the lightest part. Okay? So let's look at an example here. We're going to derive a material index for this situation. And again, remember, we have to know the function and which dimensions are constrained. Okay? So we're looking at the lower control arm, and we're saying that the function here, we know it's a suspension tie member, but the structural function is that we need to react an axial tensile force. So we're saying that we have some force here that we have to react, okay? And we kind of have a numerical value for that, okay? And so here's an example of that. It must not fail under a pull-out test, so that for the car we're designing, we want it to be 2 times the gross axle mass on this, okay? So presumably we could have a number for that, multiply it by 2, and that gives us a value for F sub r. Our objective here is to minimize the mass of the tie bar. We could have other functions. We could want to minimize the cost of the tie bar. We could want to minimize the amount of CO2 gases that were expelled when we created the material for the tie bar. Okay, so those are all possibilities. We're going to use this one. We want to minimize the mass, and we need to know what free variables can be set by the designer. So what do we have the ability to change here? And we're going to say that's cross-sectional area. Okay, so in this case, the length here is fixed. We're saying we have some really complex suspension mechanism here, and that L was established in order to get the right motion of the suspension. And the other thing we have, of course, to free variable is the material. Okay, so we want to know how to do this. Okay, so one way is just to kind of pick a material and go through the calculations, determine the cross-sectional area necessary to meet the requirement, multiply it by the density, and that would be the mass, and we could just keep doing this for all possible materials, which would be really time-consuming. So instead, we want a quicker way to do that. So let's look at the kind of the physics behind this case. So here's our little tie bar here. Length is given. We know some load that we're going to be applying, and we don't want to have a tensile failure. So here's the mass of the little bar. Cross-sectional area is this, the length, density, and the tensile strength. Okay? Those are pretty obvious parameters there. So here's the physics. We know that the stress is equal to the force divided by the area. Call that equation 1. And remember, we want to minimize the mass. So the mass is equal to the volume of the tie bar, the area times the length, times the density of the material that we had selected. So now let's take equation number 1 and put it in equation number 2. So what we're going to do is solve for A. So from this equation, we get A is equal to F sub r over sigma t. Okay, so we're just going to substitute that in there. So here's the F sub r, here's the sigma t on the bottom, and then here's the rho and the L as before. Okay. So now we have an equation for the mass, and remember we're trying to minimize that mass. So when we look at this equation, F sub r is a requirement, and we can't change that. That's a given. So if we want to minimize mass, we're not going to do it with the requirement. L, remember, is the geometry that's fixed, a given, so we can't change that, so we're not going to minimize M with that. So the variable that we have to play with is the density over the tensile strength. Okay? So if we choose a material that has the smallest value for this, that would give us the lightest weight tie bar. But we're going to just do something a little bit differently. We don't like to minimize stuff. We like to maximize stuff. So what we're going to say is we're going to maximize the reciprocal of that value. Okay, it does the same thing. It just kind of, lets us use maximize. Okay, this now becomes the material index, the tensile strength divided by density. For this particular example, becomes the material index. Okay, so right now we don't have to go through the tedium of designing a bunch of tie bars. We can just look at a table of properties, take the ratio of tensile strength to density, and then pick the one that has the biggest value. Okay, so let's do that. So here, let's kind of just first look at this. So here's several different materials. This is their tensile strength. This is their density. We just divide those two, and we come up with a material index. And remember, we want to maximize that value. So we're going to, right now, just kind of throw away the ones with the smallest values. So we get rid of those 4 materials. Now, normally we would just kind of throw them all out in one fell swoop. What we're doing is keeping some. Normally we would just say, well, carbon fiber reinforced has got the biggest value, so throw away everything, and that's the only one we want. Okay? But we're going to retain a few other ones just to kind of look at this a little deeper. Okay? But you see how easy this is when we use this idea of a material index. Now what we want to do is say, well, let's look at the cost. You know, we said we really, what we're trying to optimize is the mass, but we do care about cost. We can't have the super expensive material for most of our cars that we want to put this in. So now we're going to take and minimize the cost. Okay, and we just need one more parameter there, and that's the material cost per kilogram. Okay, so that's the kind of the usual way we think about a raw material cost, is in dollars per kilogram of the raw material. So we had this equation before for the mass. So all we have to do in order to get the cost is multiply that same relationship by the material cost per kilogram. Okay, and then that gives us the cost of the material in our tie bar. So here we're just going to substitute in for the mass. We're going to substitute in this. So now you kind of see the same idea. We're not going to change that's a requirement in order to minimize costs. We're not going to change the specified length to minimize it. So all we can do is change this parameter. And again, it's a function of material properties, right? The only thing we've added here is the cost to it. So now this becomes a material index. Remember, we're always kind of turn that over, and then we're going to maximize. This one we would want to minimize. This one now, the reciprocal, we're going to maximize. And it looks a lot like before. The only thing that's been added in is this material costs per kilogram. And again, these are all material properties. So all we did was take the material index for mass, and we replaced the density part of it by the density times the material cost per kilogram. So now we can go back to our table of values, and now I've just added in a cost per kilogram. And of course this varies a lot, so these are just kind of point values here at a point in time. So now we're just going to take the material index. This was the material index for mass, and now we're adding this material index for cost. And again, we want to choose the material that has the biggest value. So this was already kind of thrown away. But now we see things have changed a little bit. Now, if we want to minimize costs, then what we want to do is select the advanced high-strength steel arm. The one that we thought was really good before for just minimizing mass happens to be the most expensive. Okay, so we're kind of going back to this performance versus cost kind of a trade-off. So now we can kind of throw away the ones that are not really viable for cost, and we're really left with just 3 options. One here is forged aluminum, one here is an advanced high-strength steel, and then the last for supercars, carbon fiber reinforced plastic. And it's kind of helpful to plot this information. We have these material indices. We can plot these on a chart that looks like this. So along the y-axis, we're looking at a material index for mass. So as we go larger and larger with this material index, we get a lighter and lighter arm. On the x-axis here, we're using the material index for cost. So as it gets bigger and bigger, that means the cost gets lower and lower. So this is now just plotting all the information from what we had before. And of course, the best area on this chart is way over here. That's where the mass is the lowest and the cost is the lowest. And you see there's no material over there, but we do have some better materials. So if we kind of look at at this region, the 3 kind of best materials, These are dominated, so we would like never choose those. We would choose only one of these three, depending on how much we value cost. Okay, so if cost is totally irrelevant, if we're designing a supercar, then carbon fiber reinforced plastic would be the best. If we're designing a little budget car, then we would want to really have an inexpensive material, so steel would be best, and then something kind of in between, aluminum would be best. So amongst these three, it really depends on how we value mass versus cost. So how many dollars per kilogram are we prepared to spend in order to reduce the mass? Okay. So we in this little example, we derived a material index, and again, remember, it's for a particular function that we're designing for. In this case, it was a tie bar loaded in tension, and for a particular set of constrained dimensions. So the only thing that we were free to change there was a cross-sectional area. So we won't go through this derivation for other material indices, but here is a chart where the structure type is a beam, and the function, each column, there's a kind of a different function here. So if we just want a stiff beam and bending, here's the material index. If we want it to be strong in bending, we have a couple of material indices depending on how it will fail. If it's a yield stress fail, here's the material index. If it's a plate buckling, here's the material index. If we want combined kind of optimal strength and stiffness, we're going to fail by plate buckling. This is the material indices here. So you can kind of see, here's for plastic hinge, here's for an energy absorbing column. So we have these various material indices. This shows the constrained dimension. So again, we're always kind of considering, primarily a rectangular section. Here is if we're constraining both the width, the height, and the only free variable is the thickness, we would be using these. If we're allowing both T and the section height to change, then we would be using that for a material index. So these are for beams. Here's for crown panels, a different set of material indices. So let's kind of just do an example here. So let's kind of look at we did a beam before, or a tie bar. Let's do a crown panel here. So here we're looking at the kind of a hatchback door. We're looking at this lower portion, which we can kind of consider to be a panel. We want it to be stiff. We're going to constrain the width length. So here's the width and the length and the shape. So we're going to say it's a crown only. The only free variable that we're going to have is the thickness. Okay, and we're going to minimize mass. So when we go into this equation, here's the normalized stiffness. This is the material index that we want. So let's do the same set of materials that we looked at before. We've added Young's modulus here. So here is the material index for each one of these. So again, we want to always maximize this to get the lightest weight part. So which one is the biggest? Here's carbon fiber reinforced plastic. What's the smallest or worst? It would be, this is sheet molding compound, so it's like a very short chopped glass fibers, not very good. Steel is a little bit better. The next would be aluminum, and then, the next would be glass fiber, reinforced plastic, and then aluminum. Here would be second best to the carbon fiber. Okay, so again, you can kind of see how quickly you can screen materials before you really start the design process and start to put a lot of effort into sizing something. At least you know that it, you know going in if it's a well-performing material. There's one other area that I'd like to talk about that this material index is really useful, and this kind of, if you kind of look forward to the end of the semester little quiz online, this is the approach that you would use for that. So let's say we have a design sitting on the shelf. It's a lower control arm, and it's forged aluminum, and we know the mass, right? We have the hardware, we can put it on a scale. Right? And what we're considering is, well, we might want to make that, instead of forged aluminum, we might want to make it in terms of an advanced high-strength steel stamping. Okay, so this is a new design, and we don't know how much it weighs. Okay, but what we'd like to do is kind of get an estimate for the mass of this new design based on what we know about the existing design. Okay, so for each part, specific function of material index equation needs to be identified. So let's look at this. We can say it's the same that we looked at before. It's a tie bar in tension. And what we know about that material index is that the mass of the part is inversely proportional to the material index. Okay, so that's kind of the definition that we use. Okay, and in this case, for design number 1, we know the mass. We have the part, we can weigh it, and we can calculate the material index. Just substitute in the properties. Okay, so what we want to do is know what is the mass of design number 2 based on design number 1. Okay, so we can just take this equation, and when we flesh it out here, that the ratio of the masses, the ratio of the mass of this design to this design, this is 2 and this is 1, is inversely related to their material indices. Okay, so if we know the material properties for each of these, we would know these, and we know the mass of the reference design, and then we can come up with a pretty darn good estimate for what this design will be in a different material. Okay, so this is the equation that's really relevant here, and the estimate will be much better because all the other design constraints are taken into account on this existing design. Okay. So let's take a look at how this would play out. So here's our known base design, forged aluminum, so we know the material properties, we know the mass of the part. Here's the design here, and we want to know what is this design in high-strength steel. Okay, and we know this is the equation that we'll be using. This is our estimate for the mass of this. So let's take a look. In the previous example, we said that the material index was the tensile stress of the material divided by its density, and that's for a requirement that looks like this, and we're allowing the cross-sectional area to change. Okay, and we got these material indices for advanced high-strength steel, so that's just plugging in this and this into this equation, and for forged aluminum. Okay, so here's the answer. This is material index number 1. This is material index number 2. And we would find that the mass of this advanced high-strength steel lower control arm would be about 1.88 kilograms. Okay. And then we can say that presumably we would be doing this maybe to save some costs. So let's see how much cost we would save. We can just take that mass times the C sub P, and remember this is the dollars per kilogram for each material. So for forged aluminum, $2.50 per kilogram. For advanced high-strength steel, just take $1 per kilogram, so we can get some idea of how much we're saving as far as cost. Okay, so just again, use for really preliminary design, a little better estimate than just using the material index alone to actually calculate the specific mass that would result. Okay, so just what we did in this little lecture here was looked at some of the examples of materials that are used in auto body structure. It's a relatively limited list. The main contenders are advanced high-strength steel, aluminum, sheet extrusion, really, in this idea of, in some cases, combining those two materials. This is pretty rare still. Magnesium is pretty much limited to instrument panel structures. We looked at some mass benchmarking of different material options and kind of got in general how much does going from steel to aluminum, what options might that be. Came up with some regression equations that would help you calculate the actual mass if you substituted that in. Came up with the relative properties for material options. And then finally, this was kind of the really important takeaway from this lecture, is that method, this is called the Ashby method, by the way, of material selection, particularly for preliminary designs, that allows you to screen out a lot of materials very, very quickly. Okay. The last point I want to make is in this Ashby method, we use the material index, and I just gave you some charts of the material index for auto body structures. In the appendix, there are some derivations for the material index. This will never appear on a quiz, so don't worry about this from that aspect, but if you're curious as to where did these material indices came from, this shows you the basic equations that were used. Okay, so thanks a lot for your attention, and next time we'll be talking about vibration in the auto body structure.